Hi students, today we will discuss how to derive the capacitance of a cylindrical capacitor. In earlier class, we have already derived the expression for the capacitance of a spherical capacitor. Now we are talking about cylindrical capacitor. So we can understand that two cylindrical conductors will be there. One will be the inner one, other one will be the outer one. Then two oppositely charged will be developing between these two cylindrical plates. Then that forms a capacitor. So now you see how to derive. So let us consider, suppose a cylindrical capacitor having the outer cylinder of radius suppose B and the inner cylinder, that surface, that is suppose we are having that is your A, the radius will be A. Now this is suppose positively charged and the inner one is suppose negatively charged. This is suppose negatively charged. So now this is a cylindrical capacitor. Now it is a cylindrical capacitor. So to derive the expression for the capacitance of this cylindrical capacitor, what we need? We have to assume a Gaussian surface in between these two plates, and on the Gaussian surface we will find out the electric field intensity by using Gauss theorem. Then from the electric field we can find out the potential, then from the potential we can derive the capacitance. So potential, you know what is the relationship between electric field and potential? E is equal to minus dV by dr, or V is equal to negative line integral of electric field intensity. So these concepts we are going to use here. So let us consider a Gaussian surface. Suppose the radius of R, the radius of R, radius of R. So from the center this radius will be equal to here suppose R, right? So now you see here, if we consider the inner Gaussian surface of radius R, then the total charge enclosed by this cylindrical capacitor, that is inside the Gaussian surface, let that is Q. So your total flux will be equal to Q upon epsilon naught. You know this thing from Gauss theorem. Now again we know that flux is surface integral of electric field intensity. So this will come as E into surface area. So surface area, the type of Gaussian surface in this case is cylindrical. So surface area will be 2 pi r into length of the cylinder. So this will be equal to 2 pi r L, right? So this will be 2 pi r L. So similarly, if we equate these two, then we will be getting Q upon epsilon naught is equals to E into 2 pi r L. Now already you know the type of charge distribution for a cylindrical surface is your linear charge density. That means the charge is distributed lengthwise. So for Q I can write the total charge will be your linear charge density, you know, Q upon L. So in this case your Q will be equal to lambda into L. So for Q we can write here lambda into L upon epsilon naught. So this will be equal to E into 2 pi R L Similarly, we can find out here E will be equal to here 2 pi RL. This will go that side. So this is lambda L upon 2 pi RL epsilon naught. LL cancels out. So finally we'll get E is equal to lambda upon 2 pi epsilon naught. This is R. So this is the electric field intensity on the Gaussian surface. So now we want to find out the potential. So how to derive the potential? Here you know potential will be, we can find out the potential by taking the negative line integral. So your V will be equal to your negative line integral, that is E dot dr. So here you can find that E is from positive to negative, that is E is towards the center, that means the direction is like this, but whereas the radius, that is the distance, is increasing right side. So we can tell the electric field intensity and the radius, that is the distance, they are in opposite direction. So as E and D are in opposite direction, so here the angle will be cos 180. So we can write V will be equal to cos 180 means you know minus 1. So minus minus plus. So this will come as EDR. Here the distance between the two plates, how it is changing? It is changing from A to B. It is changing from A to B. So we can put the limits A to B. So now by evaluating integration, this will be lambda upon 2 pi epsilon naught R. This will be dr A to B. All the constants will be taken outside. So this will be 2 pi epsilon naught. So only the integrating term is your dr upon R. So dr upon R, you know 1 by x dx. Integration is log x. That is ln. So here we can write this one as ln s. The integration will be ln R. And the limits are A to B. Now you again know from the logarithm that the upper limit, that is ln B, and this is lower limit ln A. So ln B minus ln A. So this will be coming as ln B upon A. Right? So here we get the formula for the potential. Now you know how to find out the capacitance. So if we are knowing the potential difference, then we can find out the capacitance. So capacitance will be equal to the Q upon V, that is charge upon potential. So here we can find out your C will be equal to, that is Q upon V. So here we will be getting, for Q we can put, this is lambda into L. Now V, for V we can write lambda upon 2 pi epsilon naught. This is ln B upon A. So similarly lambda lambda cancels out. This will go above. So this will be 2 pi epsilon naught L upon, this will be ln B upon A. So similarly we can also write 2 pi epsilon naught L. If logarithm we are taking to, then this will be interchanging. So this will A by B. So this is the final derivation for the capacitance of a cylindrical capacitor. So I think in this derivation we are only using the simple concept of Gauss theorem, and the type of charge distribution for cylindrical surface is your linear charge density. And one relation we are using, the relationship between electric field and potential difference. So electric field is negative potential gradient, that is E is equal to minus dV upon dr, or we know the potential is also negative line integral of electric field intensity. So these three concepts we are using to find out the capacitance of a cylindrical capacitor. I think it is clear to you. Thank you.